Hey guys, we're back. Fred here, AF Math and Engineering. We are going to finish up this deflection by integration problem. Now I know this can appear to be, a really tricky kind of a subject. It's not. It is actually straightforward, but what you do need to do is be really, really careful with your numbers, okay? Because now you're going to see that we're going to start equating things from the first section to the second section of the beam, and you just have to make sure that your calculations are correct. So work slowly. Go step by step and you shouldn't have a problem, all right, on the test. With that being said, let's begin. So we want to find the deflection at point C or at x equals 20, okay? Or at x equals 20. And I've gone ahead and I've just made a red box around the equations 1, 2, and 3 from the first part of the beam, because we're gonna need those when we're finding the deflection between the point at B and C. So the first step is that we're going to have to cut the beam at B and C. As we talked about before, wherever we want to find the deflection or the rotation, we want to go ahead and cut the beam there. So let's start by doing that, okay? So let's draw our little diagram here that visually shows us where we're cutting. Okay, so here we have point A, okay? And we have our 398 kilonewtons going upwards, okay? We still have our 60 kilonewton. Okay, and you know what? Meters, okay? So we're just gonna call that 60x, okay? And we're going to say that this whole distance is x, okay? And we also have our point B here, right? If you'll remember correctly. We have by equals, okay, 802 kilonewtons here, okay? And well, what else do we have? Let's take a look. That's pretty much it for the external forces, okay? We do have our, because we cut the beam here, so we have our shear and we have our moment acting in this direction, okay? So it's exactly the same thing we did in the first part of the question. We cut the beam and we're just gonna go ahead and we're going to derive our moment equation from this information that we have here, okay? So let's go ahead and do that. So we have the summation of moments, okay, is equal to, and okay, we have this moment here, right? And sorry, I forgot to include this distance here, all right, which is given as 15 meters, okay? So let's begin. We have this moment right here, okay? All right, and we have this 802 kilonewton load here at B, right? And okay, so we know that this whole distance is x and we know that this is 15, okay? So this distance here is going to be pretty simple, x minus 15, okay? So what direction is this traveling? Well, this moment oriented in, it is negative. So let's say that this is an 802 kilonewton moment times x minus 15, right? All right, perfect. Now let's take a look at the 60x here, the 60 kilonewton meter load we have here, all right? And that is, the distance is x, it's the same because it's across the whole beam, right? And that is in the positive direction, all right? So let's go ahead and write that in. So we have 60x, and so the distance actually is x over 2, sorry. Perfect. And we have, again, our 398 kilonewton force upwards, all right? And that is at a distance of x from where we cut the beam. So I'm going to just write that below here, and that is in the negative direction. Okay, now if we go ahead and simplify that, so when I say that, it means just solving for this, and that is all equal to 0. So solve for the m, okay, we're going to end up with EI m equals, all right, all right, there we go. So that is, we'll call this equation 4, okay? And like we did before, okay, and you might get confused, I used m here, but m is actually d squared v by dx squared, so don't get confused by that. I'm just showing you another way to write it, okay? Let's go ahead and integrate this twice and arrive at the equations that we need to solve for the rotation and the deflection. So integrating this here, okay, we're going to get EI, and we're going to write this as dv by dx, okay? That is equal to, I'm just going to write this down so we don't waste too much time here. Okay, and that can be our fifth equation. And you know what? I wrote this as C1, but just so we don't get confused, let's write it as C3, okay? Because we do have a C1 and 2 over here, and we don't want to mix those up, okay? So we'll give that C3, the constant of integration, that's what we'll call it. And finally, for our sixth and final equation, we are going to integrate this again, okay? And we will end up with okay, let's add our C3x and our C4, okay? So we have C3 and C4 here, and this is going to be our sixth equation, okay? And let me just go ahead and give this a red box so we don't lose track of what we're working with here, okay? All right, so we've come up with the equations that we need to solve for the deflection at C. Now, we have the same problem with these equations as we did with this one, is that we don't know what C3 and C4 are. And we're always going to need to solve for those when we're doing deflection by integration. That's kind of like the trickiest part that we need to solve for. So, how do we do it? Well, see, this is a little bit different, okay? Because we don't have, when x equals 0, v equals 0, okay? So we can't just say that, for example, C2 or C4 is 0, right? Because C4 in this case isn't 0, all right? So what we need to do is we need to, and I'm going to introduce this to you now, is something called matching conditions. Okay? So matching conditions, and this can be very confusing, but just try and follow along, and if you don't get it, watch it a couple more times. Matching conditions, okay, are, you can think of it as kind of something that the two sections that you're considering have in common, all right? So what does section AB and what does section BC have in common, all right? And in this case, they have the point B, okay? So both of our sections, and if we write out 15, x is greater than or equal to 15, which is greater than or equal to 20, okay? Both of these sections include B, okay? So now we need to look at B and we need to say, what does B have in common between these two sections? And what it has in common is that the rotation, or the angle of the deflection at point B between these two sections will be the same. So what I mean by that, and I'll just use my pen as a kind of a gauge for you here, is that, okay, the angle here, all right, between, for example, if the deflection were like this, okay, this angle and this angle, okay, would be equal on both sides of the beam. That's essentially what a matching condition is. So the way we write that is that we say, okay, so EI, okay, dv1 over dx1, okay, is equal to EI dv2 over dx. And let's just say dx. Let's not write dx2. Okay, so what that means is that the rotation on both sides of this point, both sections of the beam, are the same. Okay, and we can use this, and we also have a boundary condition here. All right, and if you want to pause this video and take a guess at what the boundary condition is, go for it. It's exactly what we talked about before, all right? But if you don't, just keep following along, is that we have a boundary condition at B, okay? And that B is that at B, the deflection is 0, okay? So we can say at x equals 15, okay, V equals 0. All right, now given this information, all right, we can solve for our C3 and our C4. So let's start. So if EI dv1 by dx1 equals EI dv2 by dx2, all right, why don't we just take those from, and we'll write here 1 and 2. We can take these two and we can equate them to each other, all right? So let's start by doing that. So let's write this one first. We have negative 30x cubed over 3 plus 398x squared over 2. And we know what C1 is, right? We solved for that earlier. If you're just tuning in here and you don't know how we got C1, go back and check it out. And we're going to equate this, okay, equation 2 with equation 5. So equation 5 is okay, so that's C3 there. And so we have an equation here, okay? And we have one unknown. So using the matching conditions, we came up with an expression knowing that the angles were the same at B of both sides of the beam, and we can isolate for C3. Okay, so I'm not going to do that. But where is this, what is this X here, you might be asking, right? Well, we have all these X's in here, right? Well, we just plug in the point at which we're examining, right? Where the matching conditions are. So we can say that at this point here, okay, is at X equals 15, okay? So plug in X as 15 in here, okay? And that gets rid of that variable, and we just have one unknown, which is C3. And if we solve for C3, we're going to get a value of 83,737.5. Okay? Perfect. All right. So, what do we do next? Well, we use the boundary condition that we have, okay? When we have X equals 15, V equals 0, we went over that before. So let's go ahead and using the constant of integration that we just solved for C3, we can now solve for C4, and we're going to do it exactly the same way as we solved initially for C2, okay? How do we do that? Well, we're going to plug C3 into this equation here, or equation 6, okay? And we're going to use the boundary condition X equals 15, V equals 0, and that is going to give us our C4, okay? Well, it's not going to give it to us. We're going to need to calculate it, but it's going to isolate C4 for us, okay? So when V is 0, we're gonna plug that 0 in here, okay? 0, okay, that is equal to negative 10, okay? And we have X is 15 from here, okay? All right, and we have 600, right? Times 15 cubed over 3, all right? We have negative 12,030 over 2, 15 squared, okay? And our C3 is, it's not a good bracket, 83,737.5, okay, times 15 plus C4, okay? And if we go ahead and we solve that, you know, just go ahead and put it in your calculator. C4 we are going to find is equal to negative 451,000, okay, 125, all right? And I'll just give a black box around that, okay? So we have now, well, we used matching conditions, and what do we have? Well, we have all the information that we need to solve for our deflection at point C, okay? So I'm just gonna cover this paper up, but we don't really need it anymore, okay? Because we know that at point C, X equals 20, okay? So what we can do is, using our deflection equation, which is the one with V in it, all right, let's write it out here. We can plug in X equals 20, okay? And we can also plug in our constants. Let's do that now. So we have negative 10, okay? 20 over 4 plus 600, 20 cubed over 3 minus 12,030 over 2 times 20 squared, okay? And I'm just gonna come down here and finish this equation because it's long. We have our C3, which is 83,737.5. That's gonna be times 20, all right? And we have our C4, which we just solved for, and that's going to be negative 451,125, okay? And because V is equal to, well, we don't know what V is, right? I'm just gonna, and now we're going to solve for V, right? Knowing that EI is constant, we're just gonna carry that throughout the equation, leaving EI constant, okay? Let's do it. So just plug all that into your calculator. You know, I'm not gonna go through each step as the video will take too long, but just go ahead and do that. And at the end, we can come to the conclusion that V at x equals 20 is equal to 17,625 over EI. Okay? Now, you might be asking, why didn't I include units? Well, I didn't include the units in this just because we have an EI constant here, and usually those units will cancel out, okay, to make a unit of meters. Generally, you might have to convert it to millimeters. But in this case, I didn't include the units because we have this constant EI here. If EI were a value, I would suggest then, yes, putting the units in of the deflection, obviously, because if you don't, you're not gonna get the right answer. But I mean, this is just double check with your professor and see if they want to include the units of the numerator in here. It's really professor specific, I would say. And we have it, guys, we have it. That's essentially what we were trying to solve for, okay? So we found the deflection at point AB, all right, which is over here. We found the deflection, or B at x equals 20, all right? And that's the deflection by integration. I know it's long, it can be confusing. You have to be really careful when you're solving these types of problems, but it's not hard. You just have to kind of go through the steps, learn how to do it, practice it a bunch of times. You can watch this video a few times if you want, and just really try and understand it, guys, okay? Thanks for watching. Throw us a like and a subscribe if you enjoyed this video, and come back for more.